Hello and welcome. My name is Jackson Cox, and this is problem 1 for the ESE 403 final take-home examination. So I'm going to share my screen and we're going to get right into my solution. Alrighty, so problem 1 asks us to propose a network optimization problem and motivate its relevance. So we go here to my solution. As I said, we were tasked to create a problem that uses network optimization in its solution. And so for me, I made my problem about Tartar Farm and Ranch Equipment. This is a manufacturing company that my dad has worked at my entire life, and I actually had the opportunity of interning for them as an engineer in the summer of 2020. And so since I had a basic understanding of this business and some of the various techniques they use, I decided to make my problem about this company. And so first, if we go here into the actual problem, it says in this problem, product from Tartar Industries and Liberty Water Tank is first shipped to a warehouse distribution center until it is taken to the end customers of Tractor Supply in southern states. Additionally, some product is shipped directly from the two plants to a customer. Now, this is important information. There is no limit on the amount of product shipped from the two plants directly to the customer, but due to truck sizes, only 60 units of product can be shipped to and from each route that leads to the warehouse or the distribution center. And this final note is important. The number of products must be an integer since it is only shipped when completed. So to summarize the information to set up our network for this problem, I have created this table that shows the unit shipping costs or the weights of shipping something to and from various places. So over here we have from Tartar Industries to the distribution center, so that weight would be 4. And then as you can see, you have the various weights for each combination of paths. And then this variable down here, allocation, that is simply demand. So the demand at each node, what this node needs. And then because the customers, as we said, obviously the customers are going to be the demand nodes. And then the output from these two plants, which is Tartar Industries and Liberty Water Tank, they make products. So they have output or supply. So those are the supply nodes. Part B of the problem asks us to take this information, take our problem, and formulate it into a network model. And this is what I have done here. And as you can see, we have our source nodes here on the left. You have Tartar Industries and Liberty Water Tank, each with their various production capacities. And then you have the various paths and their weights to each of the locations. And that is, as you can see, directly from the table. So TI to TSC is 8. So you have 8 here. And from the problem we earlier, we discussed that there's no limit on shipping that's directly from a plant to a customer. So that value is infinity. This is the value of the flow for that path, or the maximum flow. And here, as we said, from anywhere to and from the distribution center, it can only be 60 units of product. So that's what is viewed here. Part C asks us to modify the network to make so we can solve it like a minimum cost flow problem. And this is more it's not a technical modification. It's more for holistic simplification so that we have one source node and one sink node. So I added source node S and sink node T just to show that, like, okay, there's one point that we're going to from, and then one point that we're going to. Ultimately, the problem solved the same way, but we add that in there to make it an official minimum cost flow problem. Okay, and so now moving on to part D. Part D asks us to propose a basic feasible solution in a feasible spanning tree, and then use that to create a linear programming model for our problem. And so basically the solution I initially proposed is find the basic feasible solution by finding the feasible spanning tree that utilizes both direct routes to the customers and the path from Tartar Industries to southern states through the distribution center. So what that basically says is I'm going to start my solution at the routes that go from TI to TSC, Liberty Water Tank to southern states, those direct routes. And I also want to use TI to southern states through the distribution center. So from this node down to this node. And so as you can see, it hits every single one of these nodes. And then obviously these are going to be hit regardless, but every single one of these nodes is within that solution. That's why it's a spanning tree. So these nodes right here are going to be our non-basic variables, or not nodes, these paths, excuse me, are going to be our non-basic variables. And so they'll be set to 0. And we'll use that to solve our solution. And so as you can see, these constraints on the left side here, this is basically the supply and demand constraint. So anything that comes out of TI has a maximum of 90, as well as Liberty Water Tank has a maximum of 80. And then anything coming into TSC from these two spots has to be equal to 70. And as the same thing with southern states has to be equal to 100. So this is just limiting the supply and demand of each node, and they have to fall within these constraints. And so since we know that TSC can only take a maximum of 70, 70 can come from TI, and therefore the other 20 that comes from TI has to go through the distribution center. So that's how we derive this constraint. As I said earlier, the Liberty Water Tank to the distribution center is our non-basic variable, therefore it's equal to 0. So all of its supply, all 80 of its units are going to go directly to southern states. So that's the value of this this path right here. And then since we already solved for this, we know that from D to TSC is 0. That's just because it's a basic variable. And then we also know that from the distribution center to southern states, it's got to be 20 in order to meet that 100 constraint. Also, this final constraint, it is redundant. However, it's just there for completeness to show that anything that goes through the distribution center in and out will be 0. It doesn't ever have, it's not an end or start point for a product. It's always going to move product out. And from the solution of these constraints, we get the minimum spanning tree, and this is what it looks like. And it is in fact part of our feasible solution. And moving on, we can now create a LP formulation using this as a starting point. So our objective function for this linear programming model is we want to minimize cost. Now, as we can remember from the table, the unit shipping cost is that value or that weight of each arrow to the node. And that total is our objective function. So we want to minimize 8 times x to TI to TSC, and that's directly from the table. As we scroll up here, this is the cost of sending something from TI to TSC. And so x from TI to TSC is the number of products. So that would be the cost, 8 times whatever we ship. And that's, as you can see, directly from that table. And so we want to minimize this this objective function, excuse me. And then while we're also still within these constraints. So these are the supply demand constraints. And then these are the constraints that all of them have to be non-negative integers. Like I said, this is an integer programming model or problems because products aren't shipped half done, they're shipped when they're done. And so they all have to be non-negative integers, but anything going to and from the distribution center has to be in between 0 and 60. 60 is our cap for those. And the best part about this is a very complicated solution or problem to solve. However, we have great tools like MATLAB that can help us do that. And that's what I was able to use. So just to simplify it, when I'm putting it into MATLAB, I converted this just the values from TI to TSC to X1 to X2 to all the way through X6, etc. And so that's like, it makes it difficult to visualize, but it was easier for me to put in. And then I'm going to pull up my MATLAB code here. We have our objective functions, we have all of our conditions, and then these equal conditions are basically summarizing all the constraints from the supply and demand nodes. And so this is just the LP formulation in MATLAB code. So if we run the code, it prints out our optimal results in order. I display the solution at the end. And so that's what I have documented here. But here I've kind of interpreted the results because I had them in order. With these results, we have the various values of the paths, and we have our optimized network solution. And so, as you can see, the optimal solution is 30 units from TI to TSC, 60 from TI to D, 40 from the D to TSC, 40 from Liberty Water Tank to D, 40 from Liberty Water Tank to Southern States, and 60 from D to Southern States. And as you can see, all of it is within our constraints, and therefore it is a feasible solution. So yes, we have a feasible solution. That's great. However, how long can this solution remain feasible? That's one thing I've learned from talking to my dad and talking to other business people is, yes, you can do all the math you want, but ultimately, when you're instituting some kind of policy in business, it is rarely exactly what you expect or calculate. So how can we adjust for changes or for maybe errors in rounding? And so that's where we perform sensitivity analysis. And so because we have so many constraints, to save time, I perform my sensitivity analysis in Microsoft Excel using their sensitivity analysis sheet. And so if I pull up here, this is exactly the same thing in MATLAB. It is just using the solver in Excel, and because they have a very good sensitivity report, and that's what I have pulled up here. And that's what I'm going to talk about in my solution. And also, like, it's much better to look at, because rather than having numbered constraints, I can actually label and describe each of these constraints. So it's kind of a better visual model of the various constraints. So if we pull up our sensitivity report from Microsoft Excel, we can see that we have the allowable increase and the allowable decrease of both the objective coefficients and the right-hand side constraints that would make our solution continue to be the optimal solution. And so my suggestion for, as far as rounding and as far as understanding our optimal solution, is definitely be conservative on the estimate of the cost. As far as, if we increase cost just a little bit by 1 on each of these, if we increase cost by 1 on each of these objective coefficients, the entire optimal solution will no longer be the optimal solution. So we got to be really, close with our cost estimate. We've got to make sure that we got the actual minimum cost. Obviously, the decrease, it goes to infinity because we're trying to minimize. So a large coefficient to decrease, that makes sense for the majority. And then also, we need to estimate these closely. So like the allowable increase is 0. So any kind of error, any small error, 1% error in the flow to and from a plant would throw off our optimal solution. So these are, I suggest strongly that we estimate the values of these constraints very, very closely. So like I said, any decrease in flow is better than an increase. Other than flow from Liberty Water Tank, any kind of decrease, it's not that big a deal so much as a great increase, because any increase would throw it off our optimal solution. And so the final part, it's similar, it's just asking about rounding. So if there's a 10% rounding error on any of these constraints, how does it affect the optimal solution? So in the case of a 10% less than estimated value, so if you calculate a value like what I just displayed and it's 10%, it's actually 10% less than what you estimated, the following, so Liberty Water Tank to Southern States unit shipping costs, that's right here, and total flow from Liberty Water Tank, that's right here, are no longer found in the feasible set, and thus the solution is no longer optimal because we have an allowable decrease of 0. So a 10% increase on 80, or 10% decrease on 80 is 8. So that makes it 70. That's an 8-step decrease. That is no longer part of our optimal solution, or the whole solution is no longer optimal because of that. And then also from total flow to Liberty Water Tank to Southern States, the allowable decrease is 1. 10% is 1. So like it's right on the edge, but it still could, throw off our optimal solution. For 10% more than estimated, we have the total flow from TI, the total flow into TSC, and Southern States are no longer found in the feasible set. So basically, if you go the flow from TI, any allowable increase 0, this is kind of what I talked about, that's thrown out because a small increase in 10% rounding error would no longer make your solution optimal. And if we look at the flow from TSC and Southern states, it's the same thing. 0 allowable increase, so a 10% on 100, that's 10 or 7. So that would then throw our solution out of optimality. I mean, also the flow through D has an allowable increase of 0. However, D is not going to change. The right-hand side will always be 0 for D because it's our distribution center. It doesn't produce anything. And so that leads us to the end of my solution for problem 1. Thank you so much for taking the time to listen, and I hope you have a Merry Christmas.